All right, so hello everyone. My name is Greg Latusinski, and today I'm going to talk about scalable edge AI benchmarking and optimization with Kenning runtime for Zephyr. So, first things first, I'm going to say about a few words about Antmicro. We are a software-driven company with extensive knowledge about how hardware works. We design hardware, we adapt Linux kernels, and prepare dedicated BSP software, edge AI deployment, and cloud solutions. So we go from the very bottom up to the cloud. And we are also advocating open source. We actively develop open source solutions. We are part of the CHIPS Alliance, RISC-V International, and Zephyr project. Now, to jump to the topic of this presentation. When we have neural network applications, the embedded platforms feel like a natural habitat for such kinds of applications. We have sensors, we have all kinds of unstructured data that works well with neural networks. They can excel at image processing, accelerometer, interpretation, and other things like that. And also, running models on edge gives us many benefits. We are independent to the cloud, so we have more secure and private solutions. We do not send anything to the cloud to do the processing. We do everything on the device. It is also more reliable. We don't rely on network connection or anything like that. Everything runs locally, and obviously it is also more scalable. However, the embedded ecosystem is a pretty harsh environment for neural networks. We have limited computational resources, limited parallelization, and extremely limited memory resources, which are the greatest pain for neural network deployment because they utilize thousands, millions, and billions of parameters in order to process data. Still, especially nowadays with the emerge of large language models, we have more and more algorithms for optimizing neural networks. We have frame algorithms for reducing the precision of weights. So instead of having 32-bit floats or 16-bit floats, we have 8-bit, 4-bit, and 3-bit integers. We also have algorithms like pruning that analyze the neural network and check which parts are necessary and which aren't, actually contributing to the final prediction, and such parts can be removed, which can reduce the numbers of filters, channels, and neurons. And there are also other techniques like low-rank approximation, knowledge distillation, or clustering that can reduce both the storage and memory utilization of the models, as well as computational time. So, to sum up, when we take a look at the neural network deployment process for the edge, we obviously, as in regular flows, prepare the model and the dataset, train the model, and evaluate it. And we do model training and evaluation in the loop until we get a well-performing model. Once we get it, we can perform all kinds of those model optimizations and compression. Those introduce some regression in quality of the models. That is why we need to keep model evaluation in the loop in order to get the well-performing model on the final hardware. And in the end, we can deploy it. When it comes to the open source ecosystem for neural networks, it is very rich, and in the same time, it has very sparse support for all kinds of algorithms that I mentioned before. They also have limited support for all kinds of platforms they can run on. Still, on the left, you can see the frameworks for training the models. On the right, you can see all kinds of frameworks that can help you optimize the model, compile the model to create a tailored, optimized runtime for your specific framework, for your specific platform. And in case there are some incompatibilities between your original tools and the optimization algorithms, there is still Open Neural Network Exchange to the rescue, which is in the middle, that binds all those together, at least to some degree. Now, the sparse support for available models, optimizations, and platforms can be troublesome. For instance, we may want to check out some new quantization algorithm that appeared in the neural network interface framework. We may want to use a slightly different runtime and check how it will work on our platform, etc. And migration from one framework to another can be troublesome and time-consuming because they have completely different APIs, they have completely different flows, and so on. To address that, we created a Kenning framework. It is a Python library for implementing pipelines for neural network optimization and deployment. So instead of focusing on specific steps or specific algorithms that optimize the model, what Kenning do, it provides the pipelines and automatization of such pipelines so that you can just replace certain blocks seamlessly without worrying what frameworks are used underneath, and then check how they will perform on the target platform. When we look at the Kenning structure, it may seem a little bit intimidating, but in general, it consists of the dataset, which grabs the dataset loading and I/O processing. Then we have models, which also have their own input processing, so scaling images to a specific size or converting the results of the final layer to predictions like object detection predictions, bounding boxes, and so on. And then we have optimizer classes that can take the data set and they can take the model in order to optimize it or compile it. And on the right, what we have is runtime execution. So what Kenning allows us to do, it allows us to run model directly on hardware and collect some necessary metrics to check how well our model performs and if the quality is well preserved. And to communicate with the target device, we use runtime protocols that can wrap regular, simple protocol communication like TCP or UART-based communication. So, to sum up the features of Kenning, what it does, it takes care for you for I/O verification, whether the inputs and outputs from various blocks match. It also performs automatic conversion of models between blocks. So for example, if the following optimizer does not support TF-Lite, for example, or TensorFlow models, it can convert first to NNX and then to PyTorch, so that it can still load the model as needed. And as I mentioned before, we have offloading hardware runtime to the dedicated machine, but we can also offload certain optimizations to target device in case we need to do some hardware-specific fine-tuning. When it comes to defining pipelines for optimization, we can do it in JSON. So here you can see how we create a model. We define a data set that is used to train and check how our model performs. Then we can have multiple optimizers, like we can first convert to TF-Lite and quantize the model, and then we can use TVM to create a dedicated runtime for our specific platform, here a regular CPU. And then we can execute the model and check how well it performs if the quality is preserved. We can also do the same with the graphical interface. And also we can do it as well in Python. But what Kenning provides, and to limit the coding, you can just pick one of the available C commands. You can find available classes, available optimizations. You can run the optimization of the model, you can run evaluation, and you can generate a report telling how well your model performed. Here you can see some examples. Kenning can give you visual reports on what instructions were used during the runtime, so you can check whether you use, for example, vector extensions for running your model. You can check the inference time. You can also compare multiple runtimes to each other. It is possible to take several sessions of Kenning and compare them to each other as shown on the left. And you also get interactive plots for such things as confusion matrix for quality or mean average precision change depending on the threshold, and so on. When it comes to supported frameworks runtimes in Kenning, you have Apache TVM, IRI, TensorFlow Lite, ONNX runtime, and some initial support for large language models. So we support pretty much lots of the existing and well-performing frameworks. And with them, we can deploy models on various kinds of CPUs, also GPUs like NVIDIA Jetson platforms, or also TPUs, in case you use Google Coral. And in general, whether the TVM or IRI or TF Lite support a given hardware platform, Kenning should too. But the above list of software hardware platforms that I listed here work with Python API. What we later did is we used Kenning and run it on bare metal RISC-V accelerator, and for that we created a dedicated bare metal implementation. But this was not enough. We wanted to have something that would actually scale up to hundreds of boards so that we can check how various runtimes and optimization techniques compare to each other on actual hardware platforms. And for this, we decided to pick Zephyr. Zephyr is a real-time operating system, highly configurable open source, which supports over 500 boards. We, as a Platinum member of the project, we support various services around Zephyr, as well as porting of hardware platforms and tool chains to Zephyr. What Zephyr does, it provides a set of sources libraries that allow to implement the same software for all kinds of targets without worrying about things like HAL or underlying toolchains and so on. In general, you implement the same software for various platforms. So the next natural step for us was to implement something which is called Kenning-Zephyr runtime. It is a unified API for evaluating and deploying neural networks on platforms supported by Zephyr. What it brings to the table is, it brings an inference library that can encapsulate frameworks such as IRI, Micro TVM, or TF Lite Micro, and allow you to test them using the exact same code. What it also provides is an evaluation app, which connects to the Kenning hosted on your PC in order to run inference on the target device and check how well it performs. So you can just plug in your board and communicate via UART and check how well your model will perform, what will be the confusion matrix, and so on. So yeah, I've already listed those frameworks, and what it also brings to the table is possibility to send the model to the device. So with the same UART communication that you use to evaluate the model, you can also send the model to the platform to check how it will perform without having to reflash the board every single time you change the model. So it is done depending on the runtime, either just by passing the byte representation of the model or by using recent linkable loadable extensions in Zephyr, so that, for example, when you have Micro TVM that provides a dedicated implementation of the model, you can just pass it to the device. And yeah, here's the example of the code. So we have simple methods for initializing model, loading it, and running inference. And to run it on STM32F Discovery, you can just build it with the following command. So you give the name of the board and the type of the underlying runtime engine that you want to use. And if you want to switch to another runtime in implementation, you just change the configuration file to tvm.conf. And same goes for different platforms and different other runtimes. The question is, what if the hardware is not available? For example, you want to test your runtime on hardware that you don't own yet, just to check if it could run. Or for example, you want to run your application in the CI. And for this, you can use our simulation framework called Renode. What it does, it emulates target boards so that you can build and run applications on Renode using the exact same binaries that you would normally use for running on hardware. So there's no need for special compilation and so on. You just take the binary and run it. And Renode has wide support for RISC-V, ARM, Power, and Spark CPUs. And what Kenning supports is built-in Renode simulation. So if you want to use Kenning to optimize and evaluate your model, but you don't own the hardware, you can just replace the runtime for the particular board with Renode runtime, which only takes the binary that is supposed to implement the given application, and then you can easily do the exact same thing that you would do with the actual hardware. So from the perspective of Kenning, it feels like it just connected to the regular hardware. It still communicates via UART or via TCP, but the device it communicates with is simulated. And what it brings to the table, in addition to just being able to check if the model would work and how it would work, it also gives us debugging capabilities. It also gives us profiling capabilities, because you can then collect information about what instructions were used during the inference, so that you can understand better how your runtime works. And it can be useful for hardware development or hardware co-design. So when you, for example, develop an AI accelerator, for example, based on RISC-V, like in case of Google, which quite some time ago released a Kelvin accelerator, which was using RISC-V CPU with the extensions, you can just simulate stuff to check how the given runtime and given hardware would perform without even building the hardware yet. And it also allows us to run inference on CI, which is used in our Renode Zephyr dashboard. Showing the preview here, what you can see is the support for various boards. There are over 500 boards total in this dashboard. And what you can see here is you can see how well those platforms perform with some sample applications. So you have applications like typical Hello World, you have Philosopher's Problem, we have compression and simple Rust application, as well as now we have also samples for running TF-Lite Micro and Micro TVM runtimes. So you can check which runtime engine supports the board of your interest, or you can check which boards you can choose to get the model and the hardware to work. And from the dashboard perspective, okay, this is not the most interesting use case. Here we have the example of micro TVM inference using Magic Wand. So here you can see micro Kenning-Zephyr runtime running Magic Wand model on some sample data Here is the output from UART. What you also get is you get trace of such execution, so you can check which methods took the longest to process in order to later optimize them. And you can also download the Zephyr binary so that you can, if you own the hardware, you can download the Zephyr binary and run it on your hardware to check how it will work. And it should just work out of the box. Right. And here's some example how this designing of the optimization pipeline actually works. Here you can see some data set that we use to evaluate the model. Here is the wrapper for the model that provides the processing functions for inputs and outputs. Here you have the compiler, which is used to run the model, and then you run the simulation in Renode. So after compiling the model, we run the simulation. Here you can see in the blue the logs from Renode that tell us how does it work from the hardware perspective, and then we run the evaluation. And the evaluation is run on as many samples as the testing dataset contains, so it may take a while. After inferring the model, you can, what Kenning does, it parses the profiling data from Renode. And once this is finished, you can just jump and click report to get a HTML generated and Markdown generated interactive report that can give you more insight on how the model worked. And this is how it looks like. So here you have the exact steps and parameters for running the optimization of the model. Here you can look up some inference time. As you can see, the plots are interactive. You can also see the confusion matrix and check which classes were troublesome or not. Here is the list of, here is the histogram of instructions in RISC-V that were used during inference. And there are also some remaining metrics, yeah, like memory utilization and other peripheral utilization. Okay, so what's next? What we want to do is we want to use linkable loadable extensions to allow you to freely replace underlying runtime engine so that you won't have to recompile the application when swapping between runtimes. Which is in the process of making. We also want to improve the profiling features, and we also want to improve the overall support for micro-TVM, IRI, and TF-Lite Micro platforms. Also, if you have a platform that you would like to add, or if you have some AI accelerator that you would like to have simulated, or if you want to have your own runtime of AI implementation tested, then you can reach out to us. We have a booth right here, and we can discuss how we can help you add your own platform, runtime, or model to work in dashboard or CI in general. So that's all from me. Thanks.